So, welcome back to your training in data science. Today, we have a very interesting topic, which is cross-validation. Our teacher and lecturer for today is obviously our amazing Scott. But before we start, we want to remind you that we know that these topics aren't actually easy, and it's very normal if you don't get it at first. So please don't be discouraged. It's a process. So be patient and kind to yourself, and with time and practice, you will get there. Now, please welcome back our beloved teacher, Scott.
Hello, everyone. Buenos dias. How are you all doing today? How are we doing in the chat? I love it. Hello, Scott with a K. This is amazing. All right. Good deal. Everyone looks like they're doing pretty well. All right. We get to work on data science 2 days in a row. Good news, everyone. I cannot tell you how much I love that show. It is one of my favorites. It is one of my favorite shows, Futurama. I find it very entertaining. All right, let me move this over here. Okay. All right, we get to work together 2 days in a row. And the two cases build on each other. So this is even better news. So yesterday's case was pretty hard. We know it was pretty hard. Hello, Hernando. All right. I want to talk about that a little bit though. I want to remind you that I've taught this. So to give you some background about myself, I finished my PhD a few years ago and worked for a while and taught at the university level and at the graduate level. And I've taught courses in this material about logistic regression before in a few different places. And one thing I want you to think about is that even when even very talented students of statistics don't get logistic regression the first time that they do it. Typically, when I teach a course about logistic regression, I expect the first pass through, maybe if I do well, 50% or 1/2 of the students will get it. And that's when I'm working with students who are native speakers of English or have had lots and lots of exposure to English. So that, there's those other barriers. Yeah, Sergio, I realized you all don't know very much about me. So I can talk a little bit about that. I did a master's degree in data analytics, and my PhD is in organizational psychology. I worked for a few years as a professor. Oh, David, thank you. Where do I turn on the line? No. Okay, perfect. Monica, did you turn that on? Show subtitles. There we go. Aha! Perfect. Great Scott. All right. So I've taught at the university level for a few years and then left that and transitioned into doing data science. And I worked as a data analyst for an insurance agency, a data analyst for organizational psychologist. Oh, perfect. Fantastic, Gustavo. I worked as a data analyst for an insurance agency. I built them a Tableau dashboard. I also worked for about 2 years for a marketing agency and did all of their analytics and data work. And currently, and currently I work for a company called Interos, and we do supply chain logistics and data science for them. So data scientists work in different spaces. The big thing that I work on is helping to build, I work in the area of reg tech and compliance tech. And a lot of the work I do is to help companies make it easier for companies to follow international compliance laws. And I do work to make sure that supply chains are more transparent. The company I work for does a lot of work to help companies unfurl all these problems that are happening right now in supply chains. I need to star again. I don't know what that means. Do I need to draw a little star on the thing? I can draw a little star. How do I do it? How do I draw a star? Where's my little annotator? There we go. Draw. Ah. Oh, nope, that's not going to work. Deja vu. All right. So I wanted to share all of that. Yes, yes, David, we are recording. I wanted to share all of that and also to tell you that data science is very hard and logistic regression is very hard. So if you finished that session last night and you were like, this is terrible, this is the worst, Scott is very, very mean, why is he doing that to us? It's okay. This kind of thing happens, and it doesn't mean to give up, it means to keep going. And I wanted to share one more thing with you from the professor, from the teaching assistants. And Oscar, do you have that quotation that you shared? Yes. Learning how to do data science is like learning to ski. You have to do it. Oh, it's not anybody. This is just hard stuff to do. So it's just statistics and data science are hard and they're supposed to be hard. So that's why data science is important and why why these things matter. There's not a lot of people in the world who can do this very important work that we are learning how to do today. So you are going to be part of a very special group of people who can do this work, and it will, change your world and hopefully change it for the better. Okay. This kind of yes, you will only be paid for data science based on how handsome or attractive you are. That's actually a big part of the thing. No one tells you that though. Yes. All right. Okay, let's go back. Let's go back and that's amazing. What? I know it's getting very bad, Marlon. This is bad. Okay. Oh no, but the more you learn data science, Daniel, the more handsome you get. Yes, everyone's horny tonight, David. That seems to be the case. What can you do? Oh, good. I'm really glad that we're recording this for DS for Columbia. It's going to be really great. I really hope they edit this part out. I don't think they will, but I really hope they do. All right. Yesterday, yesterday we talked about logistic regression, and we talked about how to use it as a classifier. And we walked through 5 steps. So the first thing we did was to perform EDA on our data analysis. And we used cross tables, we used we used t-tests, and we used contingency tests. To get some insight into the data. Next, we performed some basic statistical tests to generate some of our hypotheses. That worked out really well. And we identified a really important thing in that data set, that Simpson's paradox, that influenced the results we found. Next, we codified and tested our hypotheses with larger models using logistic regressions. So we took all the EDA work we did and we made it more formal with logistic regression. And then finally, we assessed our classifier performance using the AUC. The AUC stands for something, I don't remember what. Can you remind me in the live chat? What does AUC stand for? Viviana, perfect. Yes, area under the curve. Fantastic. Yes, exactly. Good job, Mateo. Good job, Juan. Good job, Daniel. Perfect. So I want to focus on this idea about I need to close this annotation bubble. I want to focus on this idea. Okay, remember in our AUC curve, this line right here is our random guess. This guide right down here is our naive model, where we have everything, the false positive rate is 0, but the true positive rate is also 0. It's a naive classifier. Up here, we have our false positive rate, where everything is, or our false positive rate is 100%, and our true positive rate is 100%, because we classify everything as a positive. And up here, what happens up here when the true positive rate is 1 and the false positive rate is 0? Exactly. So our AUC is trying to get as close as we can. Exactly. Very good. Perfect match. Is trying to get as close as we can to that top spot. Oh, I'm zoomed in a little bit already. That's why you guys can see everything. Okay. Let's go back down to 125. Sorry. There we go. Okay. Well, that's not going to work out super well. All right. So these are the important bits that we need. And I just disappeared my picture. That is not what I wanted. Okay, perfect. So what we're going to do today is take that core idea that we have about comparing different models, and we're going to use that and make that more rigorous. So instead of just looking at 1 or 2 AUC curves, we're going to look at a lot of them, and we're going to talk about how to make our models more robust. And do we know what we mean when we talk about this idea of robustness? Right, Matteo, that's exactly right. We want to make sure our model doesn't change when we give it new data. Viviana, perfect. Our conclusion should remain the same despite changes in the samples. We don't want to make our model too specific to the data we have. We need to build it so that it is robust, and so we have some different ways that we can check. Yes, and overfitting is very much tied into that. Perfect, Matteo. And yes, who said that? Yeah, Hair, yes, like more solid, robust, robusto, more solid. That's exactly right. We're trying to make our model stronger. And yes, Daniel, we want to make sure that we don't get too lucky with the train test split. Carlos, yes, another way to think about it is generalization. We want the model we produce to generalize when we apply it to new data. Okay, and so to do that, we are going to use this technique called cross-validation to tune our logistic regression model. Okay, so some of this will be pretty easy. The core idea that we've talked about, that is a very, very excellent doghouse. All right. So again, let's put this into a context. So load in 1 second. For some reason, my computer restarted and it looks like it didn't reload everything the way I thought it would, but that's okay. So what is our core business problem here? We want to build a default probability model that we feel comfortable putting into production. So this data is very much like the data we worked with from the lending club last night. This data is looking at defaults of loans, and we're trying to predict defaults. And I want to focus on something here. We have to put a probability model that we feel comfortable putting into production. What does that mean? How would you interpret that? This does not sound like a very data sciencey thing. You have to feel things and feel comfortable. This is surprising. Make more money. It has to be reliable, okay? Yes, we want to be sure of the results, yes. So when we talk about putting a model into production, that means that as a data scientist, we're sort of handing it off. We're saying, this is a model that's good enough to share with stakeholders outside of our company and to share with people that we want to share the ideas that we've had and the model that we built. This is making a big commitment about what we're doing. Now, but I want to emphasize this idea about feeling comfortable. Yeah, it's generalization for new data, but I want to emphasize something here. We're going to talk about a lot of numbers tonight, and we're going to look at a lot of different numbers. But at the end of the day, there's not one number you can point to and say, yes, this is the criterion. This is not like a p-value. This is more subjective. You have to use and rely on your own judgment and your own wisdom to work on this model and to think about how we would do this. So as we're going tonight, we're going to gather evidence and we're going to write down the things that we see and things we observe. And we have to be thinking about what it means to feel comfortable. Are we able to make a good judgment and a good decision about what we have, or is it inconclusive? So I want to emphasize this because sometimes people get very excited about just putting lots of numbers on top of things, and you don't always need to do that. What sometimes you need to do is look at the data you have and make a judgment call. And that's a part of your value add as a data scientist, your ability to make judgment calls based on complicated quantitative analysis. All right. Any questions about that? Okay, good deal. Sergio, yes. Your judgment is an informed judgment because you've done a lot of statistical modeling and analysis, but at the end of the day, it is a judgment. There's no perfect answer to this question we're trying to answer. Okay. So this case has 4 pieces to it. And I think this case will go a little bit faster than our logistic regression last night, because we only have 1 or 2 complicated technical pieces to explain. David, that's perfect, yes. +1. It means to validate the accuracy of the model to go into a production environment. The context of the model into the lab and going out into the wildlife of raw inputs is very different. It is important to guarantee that the model will handle in a good way and the variability and heterogeneity of data in real flow in life. Love it. You're getting the exact idea. Data science is tricky. And part of it, the reason it's tricky is it's not an exact thing. We have to use our judgment. We have to make good decisions. And we have to build things that are robust. Oh, Hillary, this is the problem. We cannot guarantee. We're making judgment calls. We can't be certain. Sometimes things break. Sometimes things don't work the way that we want them to. But we're doing things tonight that will decrease our uncertainty. We're doing things tonight that will, this cross-validation should make you feel more comfortable that your model is doing what you want it to do. All right. So we have 4 pieces, four tasks we will do tonight. The first, we need to perform some data exploration, EDA. It's time for our EDA. We're going to fit some simple logistic regression models. We remember how to do that, right? So we're going to build our logistic regressions with our swoopy curve. And then what we're going to do, and with those simple models, we are going to calculate the ROCs at the ROC and the AUC, the area under the curve, to compare those models to each other. And finally, we're going to learn about cross-validation and use this to select our best simple model. And then finally, we're going to start adding things to our simple models and testing how testing with cross-validation, how those pieces add to the model. We'll get into overfitting in a little bit. There are lots of reasons that a model can overfit, and we'll go into 2 big ones tonight. Comfortable means it works most of the time. Comfortable is like beyond a reasonable doubt. So there's no certainty with data science, it's probability. But there are things you can be more sure of or less sure of. And the goal when we put models into production is to be pretty sure, to very sure that it works. All right. So the first thing I'm going to do is load my data, and we're going to shuffle the rows. There isn't a big reason to do this, but it's nice to do because it will make sure that we all get that the answers are slightly different, which will help us with sort of testing our model. So if you notice that we are not doing the thing. Notice that we're shuffling the rows by taking a sample of the data, and the fraction is 1. So we might get if you're running this notebook on your own, you might get slightly different answers than I do. Don't worry about it. That's fine. Not a big deal. All right, we're going to use our head model. We're going to get the first 5 rows. We have 21 columns. We have a bunch of pieces of data. What can I see from this data? Well, I have some variables that look like they are, I have some variables that look like they're integers. Why is your code different? I do not know. So Julian, that's exactly what we're going to work on tonight. Cross-validation helps us get more reproducible results. So it looks like from this data, I have some variables that are floats, some variables that are integers, and some variables that are categorical. Yes, when we could control the random seed to produce the same random sequence. All right. Next thing we're going to do is to grab the keys. This is going to give us a list of the columns that are available in this data frame. This is a very similar thing to just calling dot columns, but it will give us the same pieces of information. Next, we're going to use our DF description. We're going to drop any missing data, and we're going to look at descriptions of our data set. There are 21 variables here. We don't want to spend our whole night walking through each of these variable pieces. So what I want to do here instead is just focus on a couple of things. We're going to look at the installment, which is the monthly payment owed by the borrower if the loan originates. We're going to look at the total amount of the loan, and I believe we have a measurement of income. Oh, here it is. And we have a measure of annual income. That doesn't look good, does it, Brian? Uh-oh. Can't quite get all of this onto my... Oh, well, there you go, Marlon. That sounds reasonable. So it sounds like if you remove the drop NA, I don't think it's an encoding problem. I think he's right that there is a drop NA that's causing everything to cut out. Okay, TAs, I'm going to let you help these folks who are having a little bit of trouble. I'd like to keep moving forward if we can do that if at all possible. Okay. So the first thing we're going to do right here is create a bar chart showing the number of loans that did and did not default. And I'll show you how I did it. You're welcome to do that and run that with your own code, or you're welcome to try it with Plotly or with another tool. So Oscar, can you go ahead and drop and pull and answers the first question, please? And I'm just going to leave this up here for a minute. Okay. So what do we see in this data set? What's the big thing that we notice around here? They are imbalanced. That's correct. How big is the, how big is the imbalance, Kevin? Are you going to guess? Do you want to count? Yeah, it's about 3 to 1. It's probably actually more like, yes, it would actually be. I'm curious to see if you all can. There you go. Getting lots of different answers to this question. This is pretty good. This is very. Are you all giving me odds ratios for this? This is fantastic. What we can see is about 20 to 25% of all of these of all of this data is. There we go. Thank you, Manuel. Yeah, it's about 77% of the loans are good, and about 23%, a little bit around 23% are defaulting. So this is imbalanced, and we'll talk a little bit about imbalancing tonight. I want to point out that this particular level of imbalance, about 20%, is imbalanced, and you can handle it within your model directly. When we start getting below 10% is when you need to be more aggressive about using different kinds of imbalancing techniques. When it can start having very serious effects on your model. Okay. Next, I want you to plot a histogram of the annual incomes. Mateo, it depends a little bit. I don't want to give a hard and fast rule, but we'll talk a little bit about what those imbalances look like. Generally, when you start getting below 10%, you need to be more aggressive about managing that issue of imbalance, but there's no reason not to manage it in this particular situation here. At around 25%. Okay, Kelly's catching up. Okay, how would I plot a histogram of the annual incomes? What tool do I need to do? Oscar, please put that in question 2. No, he's just gonna put it down there. Can someone answer Jaime's question? What does it mean when a loan defaults? All right, and for the rest of you, we have an annual income distribution. What can you see about this distribution right away? Yep, it's skewed left, exactly. We've got it, well, it's actually skewed right, correct? Because we have extreme values headed to the right on this particular one. It is right-tailed, yes, thank you, William. Perfect, yes, it is right skewed right, good job. It is skewed to the right because the extreme values are sitting on the right side of the graph. So we have a few people making a lot of money and the rest are bunched around here. We're going to do a logarithmic transformation to get our data to become more normally distributed. Other way around, Johan. The mean is going to be somewhere in here. Well, actually, no, the mean is going to be over here and the median is going to be right around here. You can also change the bin size if you want. But think about where the halfway mark is going to be. All the values are over 12K. I don't know what that means. Okay. So if I take a log, I'm going to use the np log function and create a distribution of this now, what happens? Exactly, Mateo, exactly, David. Yes, it's far more normal. That's exactly what we want. In general, for a lot of the modeling we want to do, we want to use data that is a little bit more normalized, and this transformation helps us talk about what we're concerned about for this particular bit. Excuse me. So let's look at question number 3. Oscar, go ahead and post question number 3 in the chat. It is quite a bit of variance. Manuel, well, I'll let the TAs answer that question because it's a little out of scope for this particular question, for this particular session. Okay, so we're going to compare the loans against the loans that are different here. So what am I doing with this data? Well, I'm using the log function. I'm creating a filter saying, give me all the loans that are not default, that are paid, that didn't default, and give me the loans that that did default. Then I'm using the .hist function, the .hist method, excuse me, on this data to plot it. And we're putting them on top of each other to see differences here. Do we see big differences in the central tendencies? Do we see big differences in these where the mass of these distributions are? Do we have one blob that's sitting way over here and one blob sitting way over here? Yeah. So do we think that there's a big, so based on what we're seeing right here, would we expect there to be big differences in income between paid and defaulters? Yes, William, we absolutely need to do a more precise test, but we also want to look at the data and get intuition about what we would expect. We're not seeing big differences. Can someone help Claudia? What's como se dice default? Por defecto. Por defecto. There we go. Wow. Okay. Predeterminado? I think we want por defecto, right? Ooh. All right. Okay. So the next thing we're going to look at, and I don't want to explore the association between annual income and monthly installment. When we talk about installment payments, is that clear what we're talking about? Okay, perfect, Kelly. So when we say installment, that's how much you owe on every month on the loan. Ivan, the installment payment is the amount we owe each month to pay off the loan. So what we're going to do right now is we're going to look at a joint plot sometimes, and I kind of want to show this. This is an interesting way to visualize the relationship between between two distributions. So what's happening here is that we're looking at the installment data and the annual income data, and we're trying to see, are they related to each other? If there is if the mass of the, oh, wow, well, there you go. It is amazing how useful Wikipedia is, isn't it, gang? Oh my gosh, let's not get into Gota again. That was wild. Okay, can someone answer Santiago's question about the installment? Yeah, Oscar, can you please post the code for the for 1.4, please? There you go. So this is another way to think about it's kind of a way to look at a scatter plot and kind of a way to think about how we would relate two pieces of data, but we can see when the scores, the density of the distributions overlap, we get a darker shade. So this can tell you a little bit about where concentrations of data are. Based on this graph, so we can see, right, there's a big count right here, and there's a big count right here. So there's a big old chunk of people that are sitting in this spot right here, which has an installment payment, probably around 300, and an annual income a little bit less than 100,000, or more like 50,000. Whereas way out here, for an installment payment of 1,200 and an income of 10,000, very, very light, no data there. Okay. So the other thing we can do here, notice this is a little bit, I'm not sure I would have done this way, but the installment payment, the distribution for the installment payment is up here. How skewed is the installment payment distribution? Does it look normal to you, or does it look rather skewed? Right, it's skewed. Yes, perfect. So it's also skewed, so we can also look at it and do a log transform on it. And when we look at a log transform of this data, what do we see? What happens to our joint plot? Yeah, Christian, the distributions are both more normal. Ah, Matteo, yeah, there's a much more positive linear relationship. It did go into a blender. But see up here, look at how stretched out it was. It was like, and that's because these extreme values were pushing up the spots here on both of these. Darker colors mean greater concentration, Viviana. So down in here, by taking the log transformation, we smush the data down a little bit, and it helps us see more clearly the relationship between these two variables. Yes, John, that's exactly correct. That's exactly correct. We can see much better the distribution of what's happening, and we also get a better sense of the linear relationship between these logs, between these log transformed variables. Perfecto. Okay. So the other thing we can do, and this is just more sort of exploratory EDA, I don't want to spend a whole lot of time on this because this guy was the big showstopper. But we do want to look at some of these other pieces of data. And again, it's always good practice to look at distributions and look at different kinds of analyses. Okay, so we're not trying to predict. Why am I okay? So let me back up. Employment length versus annual income. Why would I be interested in that? Why would I want to know about the relationship between those two variables? Economic stability. Think like a statistician, think like a data scientist. We would expect a positive relationship, maybe. Santiago, that's good. We want to see if there's correlation. We want to see if the two things are related, because what do we know about what happens with regressions when we use correlated variables in them? Well, what happened last night? What happened last night when we were looking at data and we were looking at data and we had correlated variables? It doesn't go bad. There we go. That's what I'm looking for, Oscar. I'm fishing. Yes, Marcella, that's exactly right. Simpson's paradox, and confounds. We have to really go through our data thoroughly so that if we discover confounding variables or suppression effects, or well, multicollinearity too. Good, Luis. That's a good call out as well. We'll talk about multicollinearity in a second. Camilo, I don't think the title is wrong because look at the data that's available. We are looking at loan default in line 4. Do you see that, Camilo? All right. Thank you for that excellent reminder, David. Yes, we need to be skeptical of our data. Our data is actively seeking to lie to us. So we have to be careful when we look at this data to see this. Now, based on what we see here with employment length, is there a strong relationship between employment length and the probability of default? What do you think? Yeah, not really. Not really. Good work. Okay. We're also going to look at home ownership. We love home ownership. Everybody loves to talk about it because it's when we talk about it a lot for a practical perspective because it's correlated with this. But again, income, home ownership, and employment length are 3 factors that go into credit scores and assessing credit risk. So we want to look at them and deeply understand in this data where we go. Alejandro, I'm very excited if you have an AUC of 99%, but we're not, we'll get to that in a minute. Okay. What do we see here with home ownership and annual income? And what do we see about home ownership and the relationship to default? Can someone answer Brian's question? Right, we are trying to look at hypoteca. Is that how you say mortgage? Hypoteca? No, look at what the data says. Look at the data, look at the code. What is the code doing? The code is looking at the probability of loan default. We're grouping it by home ownership, and then we're creating a bar plot of that. Oh, mortgage is hypoteca. Okay, perfect. No, that's not good for you, bro. Santiago, perfect. If you're a renter, you're more, well, no, your income is going to be lower. Yep, and your rent is going to be higher. Juan, that's actually a good question. We may have to look into that in a little bit. Why do the mortgage people have a lower DP than own? I don't know. We're gonna have to look at that. But this is, again, being a data skeptic, looking very carefully at your data and trying to assess what it means. Okay. So we've looked at some of our, yeah, I think that there's some kind of Simpson's paradox effect going on, Juan, but we'll be able to look at that in more detail in a few minutes. Or there's something weird about this data. My guess is, though, that there's something going on. My guess is that there's something unusual about these people that just outright own their homes. And so they're slightly more likely to default, but I'm not sure exactly why. And again, remember that different kinds of people get different kinds of loans. So maybe people who are getting a home mortgage are doing a very different thing than people who are doing debt consolidation and owning their home. Yeah, I don't know. We'll go into that in a minute. We really should. Someone should make that. I will give you a sticker if you make a Slack reaction with that skeptical look. All right. So another thing we want to look at here is the purpose. So this is kind of like the type of loan. And we want to look at the distribution of these types. It's weird that it rotates them 90 degrees, but that's probably for the best. And I apologize, you kind of have to turn your head 90 degrees to see what you want to see. What can you tell me about the different kinds of loans based on this graph? What is the most common type of loan? Perfect. The most common type of loan is debt consolidation followed by credit card. Do we, we probably should. That is, yeah, you're going to be doing that a few times. Yeah, that will be happening to you a few times in this one. Matar culebras, is that the word for debt consolidation? I don't know, I got to look this up. That doesn't look right. I don't think that's it. Yeah, so we can do that, 45, but it ends up creating a weird slant and it's hard to identify which bar goes to with which thing. Yeah, that's what Google Translate said, consolidación de la deuda. That seems like a very straightforward translation. I'm distrustful of straightforward translations, but maybe it works. Okay, let's continue on. So the next thing we want to look at is the default probability by loan purpose. Open a hole to fill other. I don't know what that means. Oh, okay, perfect. So up here, we were counting. We were saying how many of these loans are available in this data set. Here, we're looking at the default probability. So what looks like the riskiest kind of loan? Yeah, the other. So that's super helpful, right? Oh yeah, the most risky kind of loan is the other kind. Exactly. Sure it is. Right. Small businesses, medical debt, and debt consolidation are all neck and neck. Yeah, car loans. I mean, there are lots of companies that's what they do. They just give out car loans. Do we have microfinance on here, Elkin? I didn't see that category. Medical bills is on the rise. It's true. Well, medical loans are this like, well, you know, it's important to celebrate important holidays, Mike. Yeah, Hugo, they medical debt is a very real thing and a really unfortunate thing, and there are lots of bankruptcies in the United States that are just based on medical debt, which I don't know why we do it that way. In fact, we probably shouldn't, but that's where we are right now. All right. So the next thing I want to look at is we have some information about student loans are missing. So my guess is that either this other captures that student loan category, or more likely this financing company just doesn't deal with student loans, because there are a lot of companies that just refuse to deal with them. In the United States also, there are lots of companies that there are special banks and special financial organizations that are only allowed to deal with student loans in the US, and I think this data is from the US. Renewable energy would be solar panels or upgrades to your house. Things like sometimes you can get a loan for your house to like install heating, like solar heating, or not just heating, not just solar panels, but like insulation or energy efficient windows. People get loans for that kind of thing as well. All right. You are doing exactly what I want you to do, which is combing through this data and trying to get a really clear understanding of what's going on in it. So congratulations, my fellow data scientists. You're doing what I want you to do. Yeah, I'm gonna tell you, you can make a lot of money off of that. Okay, let's look at the distribution of jobs here. What do we see about the distribution of jobs? First of all, what's the very annoying thing here? Yeah, other. Again, useless category. Like, does not tell us a lot about what it is. Not really helpful. The next biggest thing we have is manager. Yep, perfect. I wish. But manager, right? So it looks like a lot of people who are getting loans from this organization are managers of some kind. And otherwise, it's quite spread out. Let's also look at the probability of default by job type. And again, this is a weird thing. I don't know, what is Dirk? I don't know where's Dirk's? I don't see Dirk. Clerk. Ah, yes, clerk. Scientists. Those scientists, yeah, you know how they go. They're always they're always out there. Wild. Those scientists, they live fast and they die young. That has to be like, so this is another situation where it's just like something weird is here. If I saw something like this in my data, I would be very hesitant to use the job category for that exact reason, unless I had a good explanation. Yeah, well, clearly these scientists are like getting debt so they can fund their crazy experiments. Herman, that's actually a really good point. We don't have verification on these roles, so they could be falsified or falsifications or exaggerations. So again, I would not, based on this, I wouldn't feel super comfortable about working with the loan type because we're seeing behaviors that we don't really expect and we're seeing very strange things. But we can this is a situation where we would want to where we want to go back to our data. We want to go back to our data provider and ask some questions and say, hey, what's going on here? Okay. Want to move on. Oh yeah, you could just do an H. That would be, you could also do a bar plot with an H orientation. That's a great suggestion, Abraham. So I would show them some of this, and I would show them, like, I would also want to look at like the correlation between, or like, I would do a group by and a mean and median for income against these jobs to see if they made sense. So either this is a specialized kind of organization that provides lots of loans to scientists or has some weird setup for that, or there's something funny with how people are getting classified as scientists. Or maybe something completely different. People do strange things all the time. But this is the kind of thing you would look at and say, it's time to go back to the data provider and ask some questions. And I would specifically bring up specific visualizations like this and say, we see this is counterpredictive, or this is counterintuitive, and we cannot identify through Simpson's paradox or a confounding effect that something is going on like this. So we'd want to go on. So that's what I would bring up. All right. So we're going to add a new variable. We're going to call this the install income. This is not how I would name this, but this is how the case names this. So that's fine. So let's take a look at this. So we're defining a variable called install income. What is this going to tell us? We're multiplying the data installments by 12, and then we're dividing that number by the annual income. Viviana, yes, perfect. Exactly. We're looking at the annual amount that you would pay on the loan divided by your total income. So How much do you owe as a percentage of your total income? So it's a little bit like a debt to income ratio, but it's just applied to this payment. Yes, exactly. Very good. Very, very good. Excuse me. So we're going to plot this. Oh, Oscar, good call. So maybe it is just something very strange. It's still really weird that of the 5 scientists, so that means that so if it's 80% have failed, that means that 5 scientists in the data set 4 defaulted. That's weird. That's a little weird. I'm not gonna lie. Like could be just be a small sample error, and you might just have to chalk it up to that. But something that you would want to look into. All right, we started at 8. Okay, so I want to get through just a little bit more of this, and then we'll take a short break. So what do you see about the installment to income ratio? Oh, wow. I look really washed out in that. That's amazing. Is that my owl face or is that my skeptic face? I love it. All right. So what we're going to do here, we're going to take a more discretized version of this installment income variable to see if we can get something here. Mike. Oh my God. Yeah, obviously. It's something very strange is happening with the sample. So the next step I'm going to do here with this annual income variable, it's spread out and it's not normally distributed. We're going to create these blocks here and we're going to convert it. We're going to make them a little bit more discrete so that we can get a better sense of what's going on here. And then we're going to compare them based on these loan defaults. So what do you see here? What in general is the, oh, yes. Albert, yes, that parentheses would be very important. What happened with 0.3? Yeah, Mateo, it's not a perfect linear relationship, but we really can see that as you generally increase that income, that installment income, we can see how the loan default goes up. It's pretty much in line with what we would expect with a couple of little blips here. Yes, perfect. Okay. So we have now a couple of variables. This installment income variable looks like a good idea to use in our model. We have a good sense of how some of these other variables are related to the probability of default. So we have some useful tools to track what's going on here. Let's take our next step and do exercise 2. We want to visualize the correlation matrix across all numerical features by using the SNS heat map command. And it looks like Harold and Oscar are typing now in polls and answers to give us what we need. Perfect. All right. So walking through, I want to walk through this code. Well, I don't want to walk through this code because I want to make sure we get to, I want to spend a lot of time talking about cross-validation because that's the bigger part of this case. I will say one little cheat I added in the code here when I was working on it was this anot equals true. And when I do that, notice that I can get the specific numbers here. It's a nice little tool to use to give us a little bit more information about what's happening here. I like to look at, when I look at correlation matrices, I like to look at numbers. Okay. Immediately, when you look at this correlation matrix, your eyes should focus in on something very important. And what is that thing that it should focus in on? Red squares. What is that telling you? What is that information telling you? Yep. They're correlated. Red means danger. How high is that? Okay, so two questions. Why do we care about a high correlation? Yes, why do we care about a high, yes, Javier, exactly. We're concerned about collinearity and specifically, like Diego says, multicollinearity. Brian, it's bad for our model. Perfect. Why would loan amount and installment be highly correlated? Why would they be highly correlated? Yes, the more money you ask, the more you need to pay. And there's probably a very simple formula that they use based on the number of months and the interest rate that influences that direct relationship. So these two variables have an linear algebraic relationship. Well, they don't need to have the same number of months. They just need to have the same breakout for those numbers of months. Yeah, I had to think about that as well, William, when I was thinking about this data set. Ruben, yes, you're getting it. The installment is a linear function of the loan amount. So of course they're going to have a strong linear relationship. Yep, Luis, that's very good. The loan installment is roughly the loan amount divided by the total months. Linear relationship, so we can see that. Perfect, well done. And as long as there's a general rough relationship there, we can track that. The big one I wanted to focus on was this 0.95. These others are high, but they're not. William, it's the amount of the installment, not the number of installments. Because remember, we use that installment variable to create the installment rate, the installment to income ratio. Okay. Okay, perfect. Oscar is posting some really good additional information about why we would be concerned about this. I'm really only concerned about this one that's 0.95. The rest of these that are in the 0.5 and even the 0.6 range, that's not bad. Like that for what we're doing today, it would not be great for some models, but it's totally fine for this particular model that we're doing. Okay. So our next step here, we finished part one. It's time to move to part two, building our logistic regression. So let's do some touching, like a little touch of reminder. Why would we use a logistic regression with this data? Why do we need to use a logistic regression? Why can't I use linear regression? Good, it's binary data. Yeah, we have categorical variables. Very good. Well, it's binary data and it will become a classification problem. Yes, perfect. And what is, yep. And so I can definitely look at the, I can look at the pseudo R squared and that will tell me a lot of information about this model, right? I can definitely use the pseudo R squared and get all the information I need. Nicholas, yes, that's correct. No, I've got to use the AUC. I've got to use the receiver operating curve. Yes, Sebastian, good job. I'm asking you, it's a trap. It's a trap. Thank you, Admiral Akbar. All right. Perfect. Yes. Okay. Carol, thank you so much. So again, it doesn't matter how fancy a model we build. If we don't know what's in the data, we can't do anything with it. So aligned with what Carol said, we must learn our data and get into it very well. Oh yeah, Manioso. Oh yes, a little bit of Manioso. You have to be skeptical. People will tell you things all the time that are not true. So be skeptical. I don't know what the Saleta is. Yes, Juan, thank you. Thank you for getting my reference. I don't commonly reference Star Wars, but when I do, it's always about Admiral Akbar. All right, so we're going to build our logistic regression model. I'm not going to make you watch that video. I'm even skeptical of myself. Sometimes I say things and I'm just like, Scotty, why did you say that? We're going to build our logistic, we're going to use the logistic regression function from scikit-learn, and we're going to write a function called fit logistic regression that fits a logistic regression across our set of covariates and our associated response variable y. And here is our solution, and Oscar's going to post it in the chat right now. Quick little point, logistic regression is a method in scikit-learn. Solver is a specific solution tool that's designed for bigger data sets. It's a parameter. So this is the time, ladies and gentlemen, when I would encourage you to say, these results look unusual, so I should do something. What should I do if I look at this code and I don't know what to do? Or I see something that surprises me? Yes, William, read the documentation. Documentation. For multinomial, the loss minimized is the multinomial loss fit across the entire probability distribution, even when the data is binary. So in this particular case, we want to specifically tell it to use the multinomial. The auto would probably be fine, but it's better to specify it in this case with this multinomial, which means we're specifically telling it we want to use a binary classifier. It just happens to be the way it's set up to work it. Luis, that's really amazing. That's a very cute little cute little emoji. Okay. The other thing we want to look at is Saga, which I believe is, I just had this in my brain because I was looking at this too because I thought it was confusing. Da, da, da. Here it is. For the solver, we want to use Saga. And again, because we want to be, we're working with a relatively large data set and we're going to be running it through lots of big things. Yes, perfect. So I don't think we're not actually doing elastic net regression, Manuel. So that's less the bigger piece here. Although good job of looking up the documentation and sharing that with the group. The big thing here is that we are building data sets and we're going to be running lots of subsets of those. So we want to use something that can run relatively fast, and Saga will do that for us. Again, this is getting into the very nitty gritty weeds of some of the coding stuff. That's totally fine and entirely reasonable. But yes, Google these things and look these things up. Yes, Saga Solver is still maximum likelihood. The solvers, if I recall correctly, and one of the TAs, please correct me if I'm wrong, solver sets rules about where the loss minimization function starts and how many iterations it goes through to get to a complete model. All right, perfect. So we're going to build this linear regression model. And the next step here is to create a basic logistic regression model for predicting the loan default with only one feature, install income. And remember, install income, like William pointed out to us, is the amount of the loan divided by the yearly payment on the loan divided by the yearly income of the person. Okay. TAs, other fellows, please help explain to Juan why we're using the multinomial argument. Okay. So we need to build our basic logistic regression model here. We're only going to use install income. And we're going to do a 70-30 split for our training and test validation, like right here. Notice that our training data, our training variables for X are going to be just the install income variable. And our Y variable is going to be the loan default. We're specifying we're splitting up our train and test sets here. Are we, okay. Are other people stuck on Juan's question about the multinomial arg, or do we need to go over that as a group, or can someone help him? It looks like we have we shuffled the data at the beginning, Juan. I want to make sure we have this question answered. Okay. It looks like there's still some confusion about this multinomial arg, so I do want to go back to that because I don't want you all to get confused any more than we already are. What does this multinomial class say? Okay, perfect. Multi-class, this is a parameter inside of the logistic regression tool. And we're going to go to that. So the particular thing that is happening here is this. A binomial distribution or a binomial logistic regression is a special case of a multinomial logistic regression, and it's based on Bernoulli trials. Basically, think about like coin flips. But if you have weighted coins and you do repeated trials, that gives you a Bernoulli distribution. If you have multiple outcomes you're trying to predict, you're just chaining those together. So it doesn't matter if you have two or more, it just matters that you have at least two. So basically what this is saying, so I don't think the question is about the multinomial bit. I think the question is, why is this happening? The way that this classifier is set up and the math that lives underneath it, or the statistics that live underneath it, is basically saying that if you only have two cases, just use the binary. If you have more cases, then you do the multinomial classing. It's a little confusing in the way that they set this up because we haven't talked a lot about multinomial regression yet. But basically what that parameter is saying is it's what's the word I'm looking for? It's a contingency. If you only give it two variables, it will run like a binomial classifier. But if we have more data, we have multiple classes, it will do more calculations. All right. Are we feeling better, class? Okay, perfect. Please put exercise 3-2. Oscar, will you go ahead and drop 3-2 in the poll and answer, please? It's not as bad. I mean, we haven't gotten to the really bad stuff yet, but it's not as bad. Okay. So we're going to model our fit here. We're going to run on our test variable. We're going to get convergence after 18 epochs, so 18 runs, which is pretty good. You're feeling multinomial. I'm very happy for you. Okay. So now that we've fitted a model, we need to evaluate how good it is. Yeah, the way they set this up with this parameters, they basically arrange these parameters so that this model would run because it's doing something really complicated, which is we're going to run something called k-fold sampling. Yes, Guillermo, that's correct. Oh, logistic depression, calm down. I mean, that's fair. Binomial is a special case of the multinomial class, but we usually teach it the other way around. So the way these parameters are set up, it basically says if you only have two variables for your multinomial, you have a binomial. What is parallel in jobs? I don't know where that is in the code, Mateo. Oh, don't worry about that part. I ran this with I added the verbose script here up above. Yes, which will, if the model will run for a long time, and we'll talk about how to do that when we talk about neural networks next week. But this will keep track of how the model is running. Basically, what this model ran so quickly and that we didn't really see any of these steps, and so basically it was able to run this really fast, which is basically what all of this is telling us. And there were only one job to run in parallel because this is all running on a single processor. Okay. Again, way beyond the scope of what we're trying to do today. So don't worry about it too much, Mateo. All right, for 3-3, we want to plot an ROC curve and get the AUC. And that ROC and AUC will give us what we need to evaluate our model. So we're going to import the ROC and AUC methods. We're also going to import a tool called a stratified k-fold, but we're not going to use that yet. Yeah, Alejandro, movie genre classification is a good example of that, where you might have something that fits into multiple categories. So up here, we're going to look at our ROC curve, and we're going to plot our baseline. Oscar, if you can drop this ROC business in, or if you can put 3-3 in the Slack in polls and answers tab, that would be great. We have not done that yet, actually. We will do that at a later point. All right. What can we tell about our AUC? The ROC is a visualization and the AUC is a quantitative number. So if we want to definitively say this one is better than that one, then we want a number to be able to do that. Because sometimes we need to be able to write a number and not just show graphs to show the difference. What do we think about this model, gang? At least better than random, but not super great, right? So this would tell us that using this metric, which we know has a strong relationship to our outcome, yeah, it is producing a boost above random chance, but not a big one. It is a little chueca, isn't it? Good depends on what you're trying to predict and how much information you have to predict it. So this isn't particularly good. Think about what a 0.63 says. So 50% is chance. If I told you had a coin that was weighted 60-40 and asked you to flip it and asked you to come up with an outcome for that, would you be comfortable doing that? I wouldn't be comfortable with that. Okay. Yes, Oscar, you can do you can call the summary method on this object up here to look at the coefficients and all that kind of information. All right. So in this particular case, we're going to start motivating the idea of underfitting and overfitting. Are we making good use of all the information we have in this data set? Do we have more information we could add to our model that would add to what we're doing here? Do we think we could add another variable to this model and get a better AUC? What do you think? Almost, Carlos, we need to get through this last bit, then we can stop. I know, I'm cruel. Just one more problem. Yes, we could add more variables. If we have more data we can add that we think will add value, we are underfitting our model. All right. If we put all of our data in, if we just threw in all of the variables, what would happen? What would happen if we just took every single thing in this model? Yes, perfect. Overfitting. Overfitting is happening because we're doing something called capitalization on chance. Well, Laura, how could we compare two different models and get a sense of how much our data is over or underfitting? The false positive rate would shoot up, the test set, yes. So Laura's question about how we could compare is perfect and is a great time to stop, because this is motivating our point about, yes, where you want to use a validation set. In this original example, we held out some data in a train and a test set. We're going to do a more rigorous version of that called a cross-validation. And again, we do cross-validation because we want to come to a middle ground. Overfitting is over here where we use all of the data and recklessly. Underfitting is where we don't use enough of the data and we want to get them together in the middle and get to cross-validation. Okay. I think this is a good place to stop, and let's take a 10-minute break and come back in a few minutes. Does that work for you, Oscar and Monica?
Okay, Scott. 10 minutes break. 8:35 is okay.
I think that's perfect.
Okay.
All right. Okay, are we ready to come back, Oscar?
We are set.
All right, fantastic. Welcome back, everyone. And I feel like my don't trust the hotel Wi-Fi, folks. I feel like I'm a little bit behind on the chat. All right, I'll let it load. Okay, I want to call out this question about cross-validation, but before, I'm going to put this up on the board, but before we do that, I want to pull up the specific post, that image that Maria shared in one of the threads. And I'm trying to scroll down to the bottom of my live chat and it's not letting me go there. But I want to get at something really important about why we set the RUC up. Maria, can you repost that image? Okay, Marlon, you have a good point about endogeneity bias. All right, perfect. Thank you, Maria. I'm going to drag this over here and show this right up here. And so again, I want to get into this point about how we think about the ROC curve. Down here, someone asked a really, yes, okay. Someone asked a really great question, which is why do they always start at 0, 0, and 1, 1? Well, those are two sort of extreme models, two extreme versions of a model. What's happening down here with a false positive rate of 0 and a true positive rate of 0 is we are saying that every single item will be measured as false. If the false positive if the false positive rate is 0, we can't possibly, if we say everything is false, then we can't possibly miss any false. We can't get a false positive. But we can't get any true positives either. Up here, we have a true positive rate of 1 and a false positive rate of 1. If we say everything is a positive, then there's no way everything is going to be a true positive because we're going to catch all of them because we're saying everything is true, but we are going to have perfectly false positives as well. So these are two extreme models. One is saying everything is a positive, one is saying everything is a negative. Up here is our perfect classifier. This is a situation where we have a true positive rate of 1 and a false positive rate of 0. So we're hitting exactly where we want to be. And in here, we have our random classifier. Excuse me. Where exactly the model falls based on these different pieces. So it depends on the base rate of true and false in the data. But this is the random classifier, no better than random chance. And in here, as our models get closer to touching this spot up here, they become better and we can justify and identify which models are better based on that curve. So I've explained this a few times. I'm happy to explain it again. FPR, false positive rate of 1 and true positive rate of it would be a different kind of perfect classifier. Yes, it would be a perfectly incorrect classifier. But Dorian, to your point, like you're right. Like we think about RUC really as only like the bottom half of this triangle is a repetition or as a reflection of what's on the top half. It's similar to how we think about a correlation matrix. Like we could invert it, but then we lose the sense of what true and what true and false mean, or not true and false. We get a mix up about what positive and negative mean. If we had a model that was perfectly mispredicting, that's a good model in one sense. On the other hand, that's really confusing and creates a lot of relativistic confusion, which is what we want to avoid. So we generally only think about it as, we really only think about with this AUC as happening in this top half of the triangle. Yeah, it's a little bit of a reduction to absurdity. That's a good way to think about it, Dorian. Okay, so I wanted to go over that one more time. It's really, really, really important when we do cross-validation that you understand very clearly what we're doing with the ROC and the AUC. I don't know what the AUCPR is. Okay, so I also want to go back to a question that Marlon hit on about endogeneity bias, but it looks like maybe his question got answered. Okay, I'm gonna leave that alone for now because I'm having trouble going back and forth between these different spots. Yep, Daniel, that's exactly right. Okay, so Anna Maria, I'm looking at your question. Anna Maria's question says, maybe an unrelated question. Is it possible to know all the relevant variables related to some problem all at once? How is that determined if we lack a hidden one? Residuals? What is the correct way of acting if we run out of variables in the data set to explain the behavior? So that's fair. I mean, this is a part of what happens with data science. Sometimes you have all the data you need, and sometimes you don't have a piece of data or a variable that you really need to explain the behavior in the model. Then you have to use proxies, you have to make other decisions, or you have to find a workaround. Or just say, you know, if we knew, for example, that there was information about that was here, like how many payments have you missed in the last 12 months, might be a really good predictor of whether or not you're going to default in your loan. We don't have that data. So we'd have to say, without that information, what can we do here? How can we establish this model? Yeah, this is one of those things where if you don't have data that you know you need, then it's a limitation of your model. And you can say that, that's fine. Like sometimes models don't have to be perfect. They have to be reliable and they have to convey some information. And some things are just very hard to predict. We can predict loan defaults relatively well because the behaviors that are aligned to them are very clear. We have a lot of data to test and retest. There are some problems and classifier problems that are very hard to model because we don't have a lot of good data for it. We only have a few data points. When we think about presidential elections, that's a really good example. How many presidential elections have there been in the United States? 46. 46 is a very, very small number to try and predict what's going to happen in an election. Like, it's just not there. False positive. Yeah. Genesis, I need to think through that more. Maybe David or Jaime or one of the other TAs can answer the specifics of that question. Because I do want to be mindful of time. And I want to get into these questions about cross-validation, although understanding this curve is very important. Okay. Well, he does, I mean, Richard Nixon, if he had a robot body, he would certainly have lived for 1,000 years and be continuing to run the United States today. I don't know why we love him so much. It's terrifying. Americans are very loco. Okay, cross-validation. Cross-validation is a tool for assessing how well our model will generalize to an out-of-sample data set. And we typically use cross-validation to flag overfitting. It's easy to overfit your data to a model. There is a large literature tied into the previous question about endogeneity. There's a large literature on something called the capitalization on chance. It's a well-known statistical phenomenon where statistical models try to find the best fit to the available data, but they have unique properties, like the thing we saw with the scientists, that can cause a model to be overfit, that can cause a model to say, oh, this is definitely a thing. This is definitely a pattern, and it's actually an anti-pattern. It's a problem that doesn't persist outside of this particular curio of the data set. The thing you want to Google to get a better understanding of why we worry about this is this phrase. Capitalization on chance. Overfitting is largely the result of capitalization on chance. Chance relationships in the data that are causing our model to perform better in this particular data set that will drop its performance on that will drop our model's performance on new data. So how do we deal with this? How do we adjust our model to address capitalization on chance? Well, we're going to use a technique called cross-validation. In the earlier steps of this data set, we did a very simple model. We did the train test split model. How many partitions did we make when we did that train and test? How many pieces did we break the data, or how many times did we break up the data? How many times did we break up the data? 1. Now, well, 2 pieces, but only one time did we break up the data, you see. But that's why I was careful about how I phrased my question. Do we really, in order to build a better model, what we really want to do is do that multiple times. And we're going to use a technique called k-folding. So these k sets are our folds. In the previous example, we had a k-fold of 1. Exactly, Lucy. It's an iterative process. We're going to do this multiple times. Each of these folds will be used to train the model, and the test and the held up fold will be used as the test set. For computational stability, and again, to reduce capitalization on chance, we're going to do this more than once. We're going to do this many times, such that each fold has an opportunity to serve as the test set. For each prediction, for each repetition, a prediction performance is, for each of these k-folds, we're going to calculate an AUC on that test set. Then across that test set, we're going to calculate the average of those metrics and their standard deviation to report that. Again, I would have to go back and dig deep into my statistics, but in this particular case, reporting the average is okay for this particular model, because I believe that AUCs are normally distributed, even on non-parametric data, but I have to go double check that. So it's I'm relatively sure to very sure it's okay to use normal distributions on this, and report means. Oh no. Yes, you could use AI prediction for the AUC. That's getting very meta. I like it. There is no exact science for choosing a proper K for your data set. What did we say at the beginning? Throw a dice. Sure, throw a dice, whatever. I like 10 folds. 10 folds really, it's nice to be able to cut things nice and evenly across sets of 10. But I want to highlight this because, again, this goes back into the Antonio, yes, you can do cross-validation applies to any kind of machine learning model that you would want to build. So it applies to linear regression as well. Oh, Christian, thank you so much. Yes, the ROC curve. Oh, thank God. I was really worried. I was 90% sure that it was. Oh. Okay. So people are asking a really good question. I will talk about this in 2 seconds. Let me get to this point. There is no exact science for choosing a proper K. This goes again into the idea of feeling comfortable. So, and this is related to this core question of, well, how many splits can I do? The larger your K is, the more you are reducing your chance to get unlucky. So think about it this way: the more subsets you can create and the more times you can run this test, the more likely you are to avoid unlucky, to have this capitalization on chance ruin your model. Now, remember though that there are 2 sort of costs you have to pay. One is that sometimes it can be really expensive in terms of time or money to rerun models on big data sets. And tied into Juan's question and one other question in the Slack, we want to make sure that we have enough data in each of our folds to run a statistically valid model. If I only have 100 data sets, if I only have 100 observations, and I try to model on 10 observations, that's not enough. That you're going to run into problems with statistical power. and you're going to create more problems than you solve with cross-validation. So you want to basically identify a minimum size of what you think is viable. Think about the effect size and think about your power calculation, your statistical power calculation, and use that as a reference for how you would think about building your model. All right. So this visualization right here is a nice way to think about the total number of a data set. Or excuse me, I am reading the title. This is a good way to think about how a k-fold would work. So experiment 1, we divided our data set into 5 different subsets. So if we had 1,000, if we had 5,000 records, each one of these rows would be 1,000 records. Yes, that's really good. Yeah, Genesis, that's exactly right. Good job. Good job finding that picture. That aligns well with the exact picture we have here. So we're taking a little chunk. We're basically creating subsets of our data, and each chunk is going to have a training test, a test set, and a training set. And we'll use that to validate our model. Okay, are there questions about what we're doing? Are there any questions I can answer about what we're doing conceptually? Are we clear about what we're trying to do when we build k-fold cross-validation? Okay, fantastic. Sarah, you look very, that emoji is not great. Okay, Genesis has got it. Fantastic. So Sergio's like, I'm all right now, but you got to be careful. I gotta watch this. Yeah, Camilo, typically five or 10 folds is good. No, this time I'm not trying to trap you. I'm trying to keep you skeptical, but okay. Ja. For now. I like it. All right. So let's see how we would do. How do we do this with code? Well, we're going to use the stratified k-fold function from scikit-learn. Oscar, yeah, it is actually similar to cross-validate. It is similar to Monte Carlo, but it's a little bit less. In Monte Carlo, you rerun the same, you create simulated data, and you do that thousands of times. This is not, this is cutting up existing data you have and running your same model multiple times. So slightly different. Same idea of let's run the model or let's run the thing multiple times, but different splits of how we do that. Okay. So we built our stratified k-fold with our in splits. So this is cutting everything up into those training and test sets. Next, for our k and for our train index and text index in enumerate, okay, so Juan, if I have 10,000 observations and I do 20 folds, how many observations are going to be in each fold? $10,000 divided by 20. There we go. Yep. If we have a smaller data set, we should use fewer folds. If we have a smaller data set, we should use fewer folds because we will not have enough data in there to create an effective model. There you go. Okay, data scientists, very important to check our math. Thank you, William. If I have 500 records in my sample and my base rate for my default is 20%, how many observations of default do I have in each set? Nope, not 1,000. Laura has it, 100. Is that enough? Do you think that's going to be enough to capture what you want to capture? My instinct, my gut reaction, and my judgment call would be, no, that's probably not enough. Yes. You're losing prediction power. You're not losing prediction power, you're losing statistical power, but same idea. You're reducing your ability, you are reducing your ability to detect type 2 error with smaller data sets. So you are increasing the likelihood that you will fail to identify a statistically significant result, which is not good. So in general, statistical power is a function of the sample size and a function of the sample size and the effect size, not a function of the variability of the data. A smaller data set is going to be more prone to type 2 error. You're going to fail to detect an effect when there is one. You're going to get more variable effects, technically. So you might be more likely to find you might be more likely to get an outlier, but you're going to fail. Most of the time, you're going to fail to find an effect when that one actually exists. So why would I be one? So there are two different types here, right? What's the difference between stratified instead of a plain k-fold? And why would I want to use stratified? Maybe we should back up. What is a stratified k-fold and how is it different than a plain k-fold? Perfect. Thank you very much, Harry. Why is it important to keep the proportions the same when we're doing this kind of analysis? Good. Yes. Very good, David. We want to get, yes, we want to keep balance. Exactly. We want the individual subsamples to be as representative as possible of the outcome of interest. Stratified K, we use stratified K when we're dealing with binary data because we want to maintain that sample as much as we can. Yes, we want to keep the proportions to have the proportion of the outcome variable that we're interested in to be as similar as possible across the subsamples so that we're not introducing another random variable that increases the error. Stratified K is a reasonable thing to use. Sometimes you would want to use a k-fold. You might be, what am I trying to say here? A quote unquote plain k-fold can be useful if you're doing this kind of modeling with linear regression or with an outcome variable where you don't need to be as strict about these models. One of the reasons you have to be strict with these is that imbalance is a really big problem for categorical variables and for classifier variables, right? Every single model that we're working with, logistic regression included, has problems with imbalance. So if some of my data sets are 50-50 splits and some of them are at 95-5 splits, that's going to have a drastic impact on the model. That's going to impact what we see here. The difference there is that there are also different kinds of ways you can deal with imbalance. One of those ways to deal with imbalance is to do stratified K with replacement of your subcategory. The other way is that you can use weighting. You can use a weighted imbalance in the class to make up for some of that issue and penalize basically when it misclassifies penalize the model more when it miscategorizes your low frequency result. Stratified K with replacement can be really useful. I like to use that because I think that I mean, it screws up some statistical rules. It violates some statistical assumptions, but doesn't violate others. So I like to do it. I like to use it. It's also easier to explain because then people don't ask me, well, why did you create these particular weights and why did you choose these? But you know, other people have other reasons why they do things. But yes, I'm getting very deep in the weeds about something that is not directly relevant to this, although it's generally relevant. Lisi, thank you for keeping us on point. We use stratified K to avoid bias in the model and avoid creating additional bias in the model beyond what we already have. Okay. So our stratified fold here will break up our data set into these train and test sets, and will show us how these are each fitting together. And notice the test set, basically the test sets are distinct from each other in each of these data sets. Excuse me. Our next step here is we're going to define a way to compute the AUC. We've done this many times before. We're looking at our train and test data. We're going to fit our logistic regression. We're going to use that to predict the probability. We're going to calculate we're going to use the ROC function to get our ROC curve. And then we're going to use the AUC function to get the area under the curve function. And we're going to return the AUC score, the false positive rate, and the true positive rate so that we can graph and see what we're looking at. Diego, yes, the stratify, you want to randomize your data, or not randomize, you want to shuffle your data like what we did at the beginning before you do the cross-validation, in case there is some kind of ordering effect. Okay, so let's take a minute and look at exercise 5. Oscar, when you're ready, go ahead and put that in the polls and answers chat. So notice what we're doing here. In line 5, we're creating a stratified K-fold. Number 6 is just an empty list that has a list of the AUCs that we want. For each of our K, for each of our K-folds, we're going to compute the AUC for each of those and grab the score. These underscores here are just identifying pieces of the data, pieces of the output from that function that we don't need, so we're just throwing them away. And then we're going to append the AUC score to this AUC list and return that AUC list. So this will give us a set of 10 AUC scores for our 10 folds in our model. All right, do I get? Okay, oh, never mind. I thought this was supposed to produce a picture, but it's obviously not supposed to produce a picture. So we're going to set this up and we're going to sort of group our variables together to build our model. I was being silly. So what this is going to do is basically say, here are all of the columns that are numerical columns. And when it's appropriate, we're going to convert them into logs. And that's going to be the annual income, the loan amount, and the average current balance. These are going to be our new variables that go into our X training models. And next, we're going to create cross-validation estimates for each of our AUCs for each of the single feature models. So basically what we're going to do here is say, let's calculate these AUC nested estimates, or 10 estimates for each of the single features in our model. Daniel, so the underscore is up here. The compute AUC score gives you several pieces of information, but it gives you the false positive rate and the true positive rate, as I recall. For the AUC list, we don't want those other things. We just want the AUC score. So the underscore here is just a throw it away, throw it away, throw it away. Okay. So for each key in our data numerics key, we're going to, this is going to allow us to calculate AUC curve, the AUC estimates, those nested 10 set, those k-folded AUC estimates for each variable in one of our simple models. So what's happening here? What's happening here basically is we're building a bunch of simple models, one for each of the numerical variables in this data set. Why would I want to build a bunch of simple models like this? Why would that be helpful for me? Why am I going to build a bunch of simple models and look at the AUC values for those simple models? Models that only have one variable in them. They're going to run fast. That's good. It does help us select variables because we can see the independent effect of each one. We can select the best fitting variable. Sure, that's good. Yep, and perfect. That's exactly right. They're good starting points for us to evaluate more complex models. If I just start by throwing in 5 or 6 variables, I won't know which one is having the strong. I won't know which variables are having the single individual effects. And I won't be able to estimate and say, hey, this really looks like the lower bound for the evaluation that we're getting. So good work. All right, for exercise 6, we're going to construct a box plot. And we're going to look at a distribution of those cross-validation scores for each variable and look at which ones have the most predictive power. How are we going to evaluate the most predictive power? How do we evaluate which model has the best predictive power? There you go, perfect. Yes, the AUC, that average AUC value. So we're looking at the box plots to get information about what that mean value is going to be for the AUC. And that will give us a better sense of which of the models is producing the best effect. Very good, yes, the one with the greater AUC. So let's look at those models. And again, I apologize, we're going to do this, we're going to play the, turn our heads to the side. So this first guy right here is delinquency in the 2 years. Let's start with this one over here, actually. Simple. It's labeled as a simple model, and it's the install income model. This is a model where we only have one variable, and that variable is that installment to income ratio. So just looking at that result, what can you tell me? What can you tell me about that simple model based on a graph, based on this graph? How well is the installment income model comparing to the other models? I don't know, Juan, how many Ks do we have? It's the best. So yes, perfect. It has the higher AUC and it has the best performance because it has the best AUC. Perfect, well done. Sorry, I know I'm not supposed to do that. Yes, it's the more powerful model. Yeah, it's quite a bit better, Juan, right? It's not really even a contest. Like the next best ones are these down here, and they're well below 60, and this one is well above 60. So we can go from that and say, we're really onto something here. Yeah, it has a higher impact. Good. So based on this, we know if we had to build a model that only had one feature, it is the same AUC as before. You're not wrong. Your model does look a little different than that. I don't know why that. I don't know what that's. Well, we didn't randomize the seed, did we? We didn't set the seed. So if you had a different random order for your data, you could end up with slightly different subsets and slightly different models. You're getting the same overall set of same set of analyses, though, it looks like. Interesting. Okay. Yeah, it's actually, well, it's incorporating two pieces of information and creating a new one out of them. Yeah, exactly, Harry. I think it's a different random state. Okay. So I want to go back to something that someone said. Where did it go? Alex Casiedo said, but it's the same AUC as before. We would expect it to be the same AUC as before, right? Oh yeah, that's that's not good, is it? If the AUC is below 0.5, that's a problem, isn't it? Don't want to rely on that that variable. But if the mean AUC is similar for the single model and we've cut the data set into 10 sets and we're getting a very similar result back, that implies that this result is pretty standard across this data set and we're not seeing a lot of differentiation there. So if we only are looking at one data set, one variable, we wouldn't expect to see a lot of capitalization on chance because we're not depending on interrelationships between the variables driving that. We're also not seeing a big spike. So there's not one little subset of data that's driving this, at least as far as we can see right now. As one of the TAs pointed out last night, I think it was Jaime, oftentimes outlier variables can have, or outlier pieces of data can have big influential results on your final analysis. So we're seeing that that's probably not the case with this data, but it always warrants further investigation. Yep, Christian, that's true. But we had this data in the data set. We just had to transform it. You have to create something out of nothing. Welcome to the life of a data scientist. Yeah, Sergey, that's actually a big improvement. Sergey, will you post the code so if people want to do that with theirs, they can do that? I've kind of got this set. I don't want to try to change what I've got at this point, but if you want to share, I think that would be great. All right, let's move on while he's doing that and talk about this next step. So we looked at a model that had only, were simple models that only had one variable in them, or one predictor variable. Now what we're going to do is look at a model that has all of the numerical features. We're going to carry out a 10-fold cross-validation, and we're going to determine whether this model has better performance than this single best feature model. Excuse me. Okay. So Oscar, when you're ready, go ahead and put put exercise 7 in the data set, or excuse me, in polls and answers. Okay, perfect. So here again, we're using some of the data we've done before. We're creating our full data sets. We're keeping our lone default, and for our X variable and for our Y variable, or for our X variable, we're taking all of the stuff that's not the lone default, and we're keeping all the stuff in our Y variable that's the lone default. Herman, didn't we just talk about how the mean and the median should be the same for the AUC because the AUCs approach normality in terms of the distribution across these stratified case samples? I thought we just discussed this. So in general, I would agree that like using the median is probably a better idea. But in this particular case, I think that the difference is pretty small because AUCs tend to be normally distributed. Excuse me. So we're going to run our AUC list is going to be our set of our AUC validation, our 10-fold model across that full data set. We're going to look at all the numerical data set as our AUC list, and we're going to get our model performance. So this data is going to give us the simple annual income. For this model, that is for our simple models, we have each of these individual ones with their 10 k-folds. And this over here is capturing the data set with all of the numerical variables in it. We're going to plot that all again. And what do we see here? Let's take a look at this box plot. And align with what Herman said, we will look at the, yeah, it does get better with all numerical. If the box plot is shrink, it means a better performance in the cross-validation test. The cross, yeah, so people will be getting slightly different, yeah, more, it means a more consistent result. Thank you, Santiago. People will be getting slightly different results here because we did the random fold and we did not set a seed for that. Yep, okay, perfect, good, Luis. What we are seeing a pretty consistent pattern here. You know, you don't, and I don't know why this figure has that. Am I showing exercise 8? Did I skip? No, I'm showing you exercise 7. Well, that's interesting. It looks like somehow my numbers got mislabeled or something. Not quite sure how that worked out. Okay. Well, you know what? We can see the all numerical values here. Oh my. Very fancy, Julio. We can see the all numerical, and we can see that the categorical variable, we can see that including all numerical variables creates a model with a higher median AUC as compared to the model with just the install income. So clearly these other variables are adding some kind of additional explanatory power, and our k-fold strategy, our k-fold sample with the test and training split means that this is not just a product, not just a random product of capitalization by chance. This is not just due to something special happening with this data. We're sort of accounting for that and reducing the way that that might bias our data. Okay, perfect. So after that, so I want to call this out as an important point in this case, and I generally agree with this statement here. The best practice here would to iteratively add models to the best single feature model until we reach a point where there is no significant improvement. So this is actually true. You could actually write a loop to do this and add each piece for you instead of doing it manually, which would be a really great way to do it, iterating through this. We are not going to do that because I don't want to keep you for the full 3 hours tonight, but I want to highlight that in general, what you would do is an iterative process of adding each variable one by one and seeing which ones are uniquely adding information. The only good reason, yeah, that would be the value here, the value add here. Okay. The next thing we're going to do is add our categorical variables. So we're going to look at the grade of the loan, which is the assigned loan grade feature that we talked about last night. And we're going to look at those. So remember that the grades go from the highest being A to G being the most risky. We can see a general distribution of these here. You can also do leave one out cross-validation, yes. That will create a lot of models. The AUC is not directly comparable because they're different things that are capturing different ideas. Like they're comparable in the sense that they are both metrics that seek to describe the explanatory power of something, but it would be, I'm trying to think of a good way to describe this. Just because two things have a similar ratio, and AUC and R squared are both scaled from 0 to 1, but that doesn't mean they're capturing the same thing, because they're ultimately very different models of how we're thinking about the universe of the data that we're looking at. So they're comparable in the sense that they are both the same kind of thing. They are estimates of the explanatory power of the model, but they are very different things because they are making different assumptions about how the data is being created, and they rely on fundamentally different calculations, right? So a linear regression to calculate its R squared depends on residuals. A logistic regression depends on maximum likelihood estimates and the log loss function. These are two very fundamentally different principles about how we're thinking about how we estimate how good our model fits, and those differences matter in terms of how we're looking at that. So it's comparing two different things that have very similar shapes. Okay. So I know you've all been waiting all night for me to say it. It's time for some one-hot encoding. Are we ready for some one-hot encoding, gang? Do you think you can handle this? Let's do, for exercise 8, let's turn grade into some one-hot encoding. Daniel, of course not, but what choice do I? Oh man, that was good. That was well played. Color me impressed. Color me impressed. Okay. So we're encoding these variables. You can see how we've encoded them. Notice that we're doing the drop first again, so that we are getting rid of one of those codes so that we have something that's the base rate for each of those. So we have our one hot encoding done. Yes, we are. We are scaling a very crazy high vertex. We're climbing. We're climbing. This is a mission impossible. Carolina, had you never seen one hot encoding before? Actually, I don't want to ask that. Okay, yes. Really useful to do this. Again, notice that we're dropping A, so A is the base rate, is against which all of these are being measured. We're going to add this feature to our all numerical model and investigate whether this leads to a significant increase in our accuracy. Notice we're using concat to add xfull and the grade categories, and then we're looking at the head here. We're going to do our AUC list. We are absolutely hot encoding here. German, you are incredibly fast at these memes. Notice for the cross-validation here, we are adding in this piece here, and we're going to get our AUC list, and we are going to, once again, look at our predictive model and plot these. So we have our install income, we have all numerical, and we have the all numerical with that loan grade. Oh, perfect. Well, I'm glad we were able to remind you that you have one hot encoding available to you. Truly a secret weapon, a powerful secret weapon of a data scientist. Okay, so looking at this model, what can you tell me? Did adding the all numerical with grade, did that increase the predictive validity of our model? Did we increase our AUC? Yeah, we could also do it with cat code. I mean, these are similar sorts of things. We're doing it. There's more than one way to do things. Sometimes there is a specific right way to do it, and sometimes you need to like iterate through the different processes. Yeah, you could actually do it with an ordinal feature. Oh my, cardinality, wild stuff. Got to be careful with those with cardinality data. Very scary, very dangerous. You are playing with fire, Carlos. All right. So for this all numerical with grade, I'm guessing the reason they didn't do this is because there is some kind of nonlinearity that they didn't expect. So they wanted to just use the categorical variables instead of the ordinal component, but that's how it goes. But we're getting into the weeds of an issue with the data, and I want to focus on this question about the about the AUC. What we can see here is that adding that grade variable increases the validity of our model again. We have a higher AUC, we have more predictive power. This is important to what we are doing. Okay. We're going to use another categorical variable, and we're going to look at the variable job and see what that does in terms of bringing predictive value. Again, you can use one hot encoding. You could also use cat codes if you felt like you wanted to do that. It's good to know how to do both because sometimes you need to do one and not the other. So, Carlos, when you are ready, please go ahead and drop exercise 9 in the data set, and we will go from there. And while he's doing that, let's walk through this code. For the DF job default, pulling in our lone default and our job, we're grouping by the job and the mean. We're going to sort the values. We're going to create our bar plot. And we're going to look at how this affects the results that we want. What are we seeing for the default rate for employment type? Well, we've got our issue up here with the scientists, those crazy scientists that are clearly defaulting on their loans to fund their mad science projects. We're going to use our one hot encoding approach here to pull our data in. We're going to concat our X grade variable with our job category variables. We're going to get our keys. We're going to use our AUC list and do our cross-validation to get our AUC, our list of AUC variables for this new model. And then we're going to plot it, just like we have in the past. You're more entangled than a sack full of hooks. Oh no, that's no good. The big thing I want you to focus on here is that really what we did, we used that job category variable. We created a bunch of additional columns for our field. We used the concat function to stick those grade variables, those job category variables onto our grade data set. So now we have everything in that one spot for our X data for our predictor variables. And then we ran our cross-validation analysis with the X grade job, which now has all that additional data in it. So now we run our model. And what do we see? We've got our install income variable here at right around 0.62. The median for all numerical is around 0.67. The all numerical with that grade data looks like it's right around 0.7. And the all numerical with that grade job is also right around 0.7. So what do we get? Did adding this data about the job description improve our result? I have two very different opinions. Okay. It doesn't seem to add much, does it? So when we're building a model, it also takes, part of the reason I'm not doing this live, not running this code live, is because it takes it a hot minute to do this. And I respect your time enough not to make you sit here with me while we watch Python code run. So what you see here is that these two, we're really not adding very much. Now, in terms of when we build models, we in general, we want to keep them as simple as possible. So I'm a good teacher because I don't make you sit and watch me run Python. Yes, that is all I have to do. Cross. We're having a Star Wars day, aren't we? We are really having a Star Wars day. I love it. Akbar and Yoda. Okay. This doesn't really add any information. So we don't want to keep it in our model largely because it's not telling us anything. It's not adding any new information. Right, it does not add info. Now, here's the thing. Just because it doesn't add information in our predictive model, that doesn't mean we should include it and keep collecting it. It may have other utility in other spots. So it's important to remember, just because a variable doesn't predict something in your model, it doesn't mean it's useless data. There are other ways we may very well be able to use that data. It may be very useful for us to look at that and understand use that data to look at demographic data and build cluster analyses with it. Think about how we build marketing segments. Yeah, exactly. Or it might be useful for product development. Perfect. Like there are other domains in which that job data might be useful. It's not useful for this model, so we don't want to include it. That doesn't mean it's useless. All data is useful. And your job as a data scientist is to figure out when and how data is useful. Karen, you don't have to have an established cutoff point to calculate the AUC, but think about what a random chance model would do. A random chance model tells you, so at an AUC of 0.5, that's a random chance model. Half the time it's right, half the time it's wrong. If you have a model that's worse than chance, you would say, it's not really good. So it doesn't rely necessarily on that sense of, we got to have a cutoff score, but you can benchmark it. And again, part of why we're doing these models is to create these benchmarks. So we know that everything below this 0.5, we can just throw away right out the gate. Up here, adding this additional information, we can, what was I saying? We know that our single best predictor, if we just had a really simple model, it gets us to 0.63. So that gives us an additional, here's the next best thing. If we just had built a really, really simple model with one data point, we could get to 0.63. So we're sort of, AUCs are complicated complex, excuse me, not complicated, they're complex because we have to create sort of our own benchmarks of here's what we can actually achieve with this data. Luis, that's great. Yeah, those last two should be ambiguous, and they are just like this. They're also ambiguous in this data. We would expected that. Yeah, I don't want to comment on that right now with respect to Python and R. We don't really want to apply significance testing to this particular thing. That's not going to help us out a whole lot. Number one, people don't do it. Number two, to calculate the significance test, we would probably have to do some bootstrapping, and that's kind of what this is doing already. So technically, like if you would run this bootstrap, you could run this hundreds of times and bootstrap out your confidence intervals to give you a parameter estimate, but we don't necessarily need that for what we're doing here. It's okay to just compare these statistics without using those distributions. You can. I'm sure there is some very, very excited statistician out there who is very busily designing a significance test to compare AUC distributions, but you don't need to do that. Okay. Is correct? Eliminate the last variable. Carlos, yes. So let's talk through Carlos's question. Carlos says, is it correct to eliminate the last variable because of the scatter of the box? What do you think? Can we eliminate this last one? Yes or no? Let's talk about Carlos's question. We have Oscar. Can we get a poll about this and polls and answers? Because I think we have some confusion here. Based on the data, can we eliminate the job variable from our classifier? I want yeses and nos. Oh, perfect. Yep. So go over and polls and answers. I want to see if we're grokking this. Oh, okay. Some people are aligned and some people are not. We can try, they say. Okay. Got a couple of no's. All variables are necessary, Ricardo says. Okay, I'm letting I'm letting a little silence hit just so I can see where we are with some confusion from this job category. Okay, so we have a handful of people and we have a bunch of people that have decided frog knife is the correct emoji response. There are no knives or frogs in this model, mercifully. Okay, so when we're looking at these models, let's hone in on this. Can I zoom in on this thing? So very big. Okay. Would like to make a point. Okay, yeah. So Christian, you have a good point. Like significance matters. Alberto, yes, that's exactly right. So the question here is, can we eliminate the classifier? Can we eliminate the job category from our classifier, from this classifier model that we're building? And the answer is yes. Now look what's happening. With all of our best models so far, which is using all the numerical data with that grade variable, And we are getting that median value, that little squiggle, that little line right there. It's not worth it. Yeah. It's really not adding any meaningful. We're getting to this 0.7 value. When we add that job data, we are still at 0.7. So we're not increasing our predictive power by including that in the model. Now, there are a couple of important caveats to this. So the general answer is a yes, but. Can we eliminate this variable from our model? Yes. Big caveats. First caveat, just because it doesn't predict something in our model does not mean it's not important. Even data that isn't predictive can still have value in other aspects. It can be we can keep it for reporting, for compliance. We can keep it for other kinds of statistical analyses, but it's not useful in this data set. Second caveat, aligned with what Christian said. So Matteo, we're just not even going into interactions yet. That is a nasty beast that we are not, that I'm not ready to dive into. Christian and Matteo both make it points though, that if this variable had some kind of nonlinear interaction with the other variables, then we would still need to include it. But right now, it doesn't. So Juan, this is important. Like in this particular case, we don't care a whole lot about the dispersion. We're running these multiple models to create dispersion because we really just want an estimate, that middle estimate from the set. We want to run it 10 times to see if we can find really, like, we don't necessarily need to remove something just because it has a lot of dispersion. We really only care about this middle value. So Guillermo, yes, that's exactly what we're doing. The k-fold analysis that we're doing and running this and taking the mean from those 10 is how we're accounting for that overfitting. If we need to choose just one of these variables, what is better? You can think about the variability in the box plots in a qualitative way and say, if there's more variability, that means there might be more capitalization on chance, or that the results are just a result of random variation in the data. But again, that's why we run it 10 times so we can get an estimate of that. I don't think it in and of itself is a good reason to throw something out, but if I were maybe weighing two variables against that, I would think about that. But again, we don't have to think about that with this job grade because it's literally not adding any predictive value. So dispersion does matter sometimes, but we don't need to use it as a decision, as a rule for including or excluding a variable from this model. Okay, I'm going to shrink this back down a little bit. Yeah, no, it's important to get this down. It seemed. So that's actually a good point, Marlon. In our particular data set, we didn't have overfitting. We would identify overfitting if we saw a pattern where for the train and the test sets, there was a significant drop from spot to spot. So if each time we were running our model and our train sets were smaller, if the validity or the AUCs for our train sets were smaller than they were for the test sets, that would give us a reason to be concerned, but we didn't observe that here. Okay, maybe grade and job are correlated. There could be correlations between the data sets. Diego, you can go check that empirically. Perfect, David, that's exactly right. Thank you for clarifying that. So we aren't observing overfitting in this data set. If we were observing overfitting, we would see these models going down in performance as we were adding more data, or we would see big differences between the train and the test results. Okay, Matteo, robustness is what we're trying to achieve here. And robustness here is making sure that our data set, our model, generalizes. So being able to say, we ran this data model on this data, and we can now use this model again on new data that this model hasn't seen before, and it will produce good results. That is the key thing that we're trying to capture. And that is a great segue into our key points and takeaways for the evening. Okay. So I'm going to ask a dumb question. I promise this is not a trap. What was the first and most important thing that we did tonight? EDA, that's right. Perfect. We did exploratory data analysis, so we had a better sense of what was going on in this data set. And again, part of that was doing our log transformations. Our next step was starting to build models, and we started with our very simple logistic regression models. Why did we need to build so many simple regression models? Why was that important to what we did? Why do we need to build a lot of simple regression models? Perfect, to compare performance, right? We need to set lower bounds and upper bounds on what we think that what we can realistically get from this data set. Very good, Laura. And David, please, everybody take a look at the article that David mentioned. Robust or robustness refers to the strength of our statistical model, tests, and procedures according to the specific conditions of the analysis. So if a model is robust, in this case, okay, Marlon, that's an excellent question. Why do you think we used logistic regression tonight? So Marlon is asking, why would we use logit as a baseline model and not random forest, for example? Mm-hmm. Manuel's got 90% of it down. Random forests are, I want to point out, we had a lot of trouble with logistic regression. You all would have like flown to DC and murdered me in my sleep if I made you learn random forest before logistic regression. So we know we can't estimate a linear model based on this data set. I want to just focus on logistic regression rather than random forest because the jump from linear regression to logistic regression, they're both still regressions. You're still drawing a line of fit and you're still drawing a single line and you are still using basically linear relationships between variables. Random forests and decision trees have a fundamentally different paradigm for how they calculate. So the big difference between OLS regression and logistic regression is they use different functions. Logistic regression uses ordinary least, linear regression uses ordinary least squares. That's that point where we said, hey, here are dots on a line, and we try to minimize those residuals. Logistic regression draws a line and says, hey, how can I draw my line to go through as many of these points as I can to create maximum likelihood? Yeah, Saturday, random forest is the next step. So random forest relies on a fundamentally different paradigm. I wanted to ease you into a logistic regression, and starting with linear regression, then going to logistic was the way to do that. Next, we'll start talking about forest, and we'll start talking about those classifier methods. That's a different creature. Periando, I don't know what that is. Is that bad? Is periando bad? Okay, I'm looking at what Genesis posted for these different pieces. Yeah, that's I would need to look at that more carefully, Genesis, but that looks generally on point. The other big reason that we talk about logistic regression is, again, we have interpretable coefficients, right? You can point to numbers in your model from your logistic regression and say, here's what this model is doing. I can turn that into an odds ratio, and I can turn an odds ratio into a probability. That will not be possible with random forests. They have a fundamentally different paradigm. They have a nonlinear relationship, and they are going to require a totally different set of assumptions than what we've been working with linear and logistic regression. Oh, twerking. Oh, I'm sorry, your eye is twerking. That sounds very painful. Okay. Excuse me. So I want to back up. I got a little down. We wandered into a little side path. We want to get back on the trail. We used cross-validation approaches to build our more complex models and looked at interactions between these features. Okay. Juan, this is an excellent thing to look up. It is very easy to calculate, to look up logistic regression coefficients and how to convert them into probabilities. Yeah, that's not wrong. Okay. Our data set contained a lot of different covariates, so we wanted to use cross-validation. When we have lots of covariates, we have to use cross-validation to figure out which ones are going to add predicted value, and then again, using our train and test, our training and test sets in those cross-validation samples to look at the AUC curve and make sure that we were not engaging in capitalization on chance. We had to make sure we just weren't getting lucky with our model. Basically, we don't want to leave our models up to luck. And again, I really like the point here. We want to choose an appropriate model we feel comfortable with, that balances complexity with accuracy. So we want to make sure we're producing a model that's accurate based on the data we have, but is not overly complex. Okay. Cross-validate, and I don't necessarily need to read this last little bit for you. Accuracy in a broader technical sense, not in the accuracy and precision sense. Okay. Okay, so last two takeaways here, and this highlights again something that I said earlier in the night. Logistic regression is one of many classification methods. You have now sort of learned how to use logistic regression to do classification. Keep in mind they are two different things. And the principles behind cross-validation don't just apply to logistic regression. You will use cross-validation again and again and again in all the models you build. So make sure that you learn this material well, make sure that you practice and work with this. Being able to do robust cross-validation, I'm overusing the word robust, being able to use cross-validation to identify robustness is critical. Okay. I think I've said pretty much everything I want to say. If there are other questions we want to. Okay. If there are other questions we want to get into, we can do that. But I think at this point, I'm ready to stop the recording, Oscar.
So thank you very, very much, Scott. We know this lecture has been, like difficult and long, but we hope our fellows actually learned a lot. So remember, guys, you always have the chance to review this material once the recording is uploaded. So without further things to say, thank you again, Scott. We wish you a great night. And hey, guys, let's go and get some sleep.
Absolutely. Thank you so much, everyone, for being wonderful. It was wonderful to be here and get the opportunity to teach you all. I will be back, I think, next week for discussing neural networks. I think that's right. So I will see you all again soon.
Yes, and we will be waiting. Bye,
All right,
guys.
sounds
Thank
good.
you, Scott. Bye.